All right, welcome back. Week 5, video 3, the last video of this week. And this time around, we're going to talk about an application of some of this Fourier business, some of this relation between so-called frequency space and the time domain. A very important application that has to do with the coherence, the degree of coherence of a light source. For example, this laser has some spread of frequencies in it. And the light from the sun has some spread of frequencies in it. And that corresponds to a time domain description as well. So we're going to build up a picture that'll get us there. Okay, so let's start by asking what is the length of our nice monochromatic plane wave pulse that we've been studying so far. Remember our plane wave, our monochromatic plane wave, it was cosine. We found it was cosine of kz minus omega t. We'll just concentrate on the frequency part right now. And in the time domain, it was just look like this. It was a cosine. It goes on forever in each way. Now, in the frequency domain, we found that we could just represent that as a single point at omega naught here. Okay, so if the time domain was a cosine of omega t, really this is a delta function. It is 0 everywhere. All the energy is contained in an infinitesimally small window around omega naught. And what is this really telling us? That if I constrain my frequency space to a point, a single frequency that's monochromatic, this corresponds to a cosine wave which goes on forever. In other words, an infinitely long time signal corresponds to an infinitesimally short frequency signal. No spread in frequencies. The only way that we can get a monochromatic wave in nature is by making it infinitely long, and therefore infinitesimally small in frequency. So this is the picture that we have relating the time and the frequency domain. Now here's an interesting fact. We have a Fourier duality here. That inverse Fourier transform that we did last time, that has the same form as the Fourier transform. In other words, what we can do is I can swap these two pictures. I can, instead of time, let's just pretend that this is actually the frequency domain, an infinitely long spread in frequencies, and that, in this picture, will correspond to an infinitesimal point in time, t minus t naught, I guess. So that means if I have a infinitesimally small, like a blip, an instant of light that just pulses on for, a blip of a fraction of a nanosecond, that corresponds to an infinitely wide set of frequencies, right? So there's this duality here. I can look at these time and frequency as two sides of the same coin. I can flip the axes because the Fourier transform and inverse Fourier transform are really telling us the same thing, okay? So this is telling us that if I have a blip in time, I have an infinite spread on frequency, and vice versa. What about things which are finite? Okay, so let's look at the width of a finite pulse. And in general, we're going to look at the mapping between the frequency domain and the time domain. Now, we can choose any kind of pulse, but we're going to choose a Gaussian pulse, because it's nice to deal with mathematically. And we're going to look at many different types of pulses, but for simplicity, we're going to look at a Gaussian. Remember what a Gaussian is. It's e to the minus something squared. So in time, it would be t minus t naught over root 2 sigma. This term is called the standard deviation, and maybe we'll give it some amplitude. That looks like this bell-shaped curve that has a spread, a half width given by the standard deviation. So the spread in times is given by the standard deviation. Okay, so we can see when t minus t naught is, it's not a Gaussian. I better square this or else it blows up. Okay, that's a Gaussian. I forgot to square it. So when t minus t naught is equal to sigma, this goes to 1 over the square root of e, it turns out, which is just a way to tell us the width of this pulse. I can perform the Fourier transform on that, and you guys get to do that on assignment 3, so I won't spoil the fun, but this is what you get. The Fourier transform of a Gaussian is another Gaussian. Okay, and if we look carefully at the standard deviation of that new Gaussian, we find that it's 1 over the standard deviation of the original. So the Fourier transform of a Gaussian with standard deviation sigma or delta t is another Gaussian with standard deviation in frequency of delta omega is equal to 1 over delta t. Okay, so that's a very important fact. This is actually a fundamental relation that we have to have delta omega times delta t is greater than or equal to 1 here. In fact, the Gaussian is a special case. It's the minimum spread. Any deviation from that Gaussian will lead to this product delta omega times delta t is greater than the original, greater than 1. So this equality holds just for Gaussians. And this should remind us of something, actually. In fact, quantum mechanically, what do we call the energy? The energy quantum mechanically, well, the energy of a photon, remember, it was h bar omega. So in general, an energy spread, h bar delta omega, times delta t, is what we call delta E delta t. If that's greater than or equal to 1, this is greater than or equal to h bar. So this is really like a Heisenberg uncertainty relation, if you've seen that before. It's a property of waves such that if you try to squeeze the frequencies too much, it spreads out in time. If you try to squeeze in the times, it'll spread out in frequency. So this is, you'll see this quite a lot in physics. And one other thing I want to point out in that is that for these temporal domain pulses, things that are moving at a constant speed, the speed of light, we can also talk about this not as just as a delta t, but we can also talk about this as a delta L. Delta L is equal to c times delta t, right? So if I have a pulse that has an envelope like this, and that's delta t seconds, in space, this is going to be L is equal to c delta t. Delta L, we'll call it. Okay, so there's this relation here. So just to see what that looks like, let's look at our Gaussian pulse here. And I'm just going to take the Fourier transform. I've done some Python to numerically do the Fourier transform of whatever we put into it. And we'll see that as we make the pulse wider, we get to better approximation to a monochromatic beam. If I try to squeeze it in time, the frequencies spread and vice versa. So you can really see this inverse relation between the spread in frequencies and the spread in time. And this doesn't just have to be a Gaussian. For example, here's a triangle wave, and we'll do the exact same thing. We get some squiggles at the bottom. Delta omega delta t is greater than 1 here, but we have the same overall form, which is great. And here's our square wave with our sync that we've calculated last lecture. You get some weird aliasing thing. It looks like it has legs at the bottom, but that's just me not taking enough points in my Fourier transform. The point is it's the same overall pattern every time. The longer in time it is, the more tightly I can constrain the frequencies, and vice versa. If I have a very short period in time, we have to have a spread in frequencies. Okay, so now I want to relate this to something interesting we found out last time. If you recall, we had this superluminal or supposedly superluminal group velocity near an atomic resonance. Right? We had something like this. Our pulse with no atoms there should have been there, but it looked like it was further along than it should have been. But really what it is, we argued that it was absorbed in a funny way. It took the dipoles a little bit of time to catch up, so that by the time the pulse had started going through, they finally caught up and we attenuated the end of the pulse. So the peak of the pulse advanced faster than it would have were there no atoms there. But of course, like the bleeding edge of this thing here, there's no extra information conveyed faster than the speed of light. And we can see this now with our new powerful method of our duality between the time and frequency domains. Okay, so the whole idea is that if we have a very fast pulse, things that happen quickly before the atoms can respond, that corresponds to a wide spectrum. So here's our absorption that we derived using the Lorentz model. We had this Lorentzian curve, and I've sent a pulse through it. The same pulse that you saw in the last video, very roughly in terms of the spacing. And we see something. Because we've made a very short pulse instead of a long or even constant field, that corresponds to a range of frequencies. Some of these frequencies are inside the absorption region of this atom. Some of them leak out. So there's regions around the tail and the head of this pulse in frequency space that will not get absorbed. And it is precisely these frequency components that make up this part of the light which leaks through before getting absorbed here. So this is very powerful. We have two equivalent ways of talking about physical processes now, time domain and frequency domain. And they lead to different descriptions and different intuitions, but they're mathematically equivalent. Right? In the time domain, our dipoles took some time to respond and catch up before they could emit fields which destructively interfered with the incoming light, leading to absorption. That's fine. But we can look at it spectrally in the frequency domain, where we just have a mismatch, which we call a spectral mismatch, between the range of frequencies that the atom can absorb and the range of frequencies that we send in, right? Two sides of the same coin. This duality is very useful, and it's going to help us a lot in optics and in other courses. Okay, great. We can go further with this. Okay, so the converse is true. Remember, we have this is all happening inside of our two-level atom here, which we modeled as masses on springs. But can I be honest, the way that we talk about it usually is a two-state system. Photons can couple, well, we'll call this the ground state and the excited state. This is the quantum mechanical analogy of our Lorentz model. Amazingly, we get the same answer for the susceptibility and all that. We send photons in. There's some rate, gamma, at which the photons leak out. Okay, so imagine we really tune this process down, so we're just looking at individual photons of light being emitted from this oscillator here. How long are they? How long does one of these photons last? Or how long does the field of this decay that we described in our Lorentz model last? What is the time duration of these photons? We have an answer now. It is a Fourier transform of the range of frequencies that the atom exists at. Right? There's this line width, and we have this spectrum. That's going to be the spectrum of the light, and therefore we know the time domain picture of it as well. All right, so we can absorb the incoming light as it is absorbed by the atoms, or conversely, we can understand the emission of light by the atoms, both in terms of its natural line width here. And this has been done. So here's a couple of pictures of that. These are pictures of light, of a single photon emitted by a cloud of atoms, one photon at a time. This is actually a picture from my PhD thesis back in the olden days. But what we did is we had photons that were detected one photon at a time. We took a bunch of statistics and looked at the different arrival times and kind of made a histogram of the shape of the photon, the temporal shape of that light that's emitted. And we have this picture here. So we can see that the spread in frequency is a few tens of nanoseconds. So the bandwidth is 50 to 100 megahertz in this process. All right, but this is a direct correlation between the line width that we're looking at and the actual photons. Okay, so let's move on to the last part. I want to talk about something, another insight that this leads. Remember those atoms that each had they're emitting photons. Each of those atoms was emitting a photon that wiggled for some amount of time. So there's a kind of a coherent plane wave that lasted for some blip of time. What about light that is emitted by many, many, many atoms at once? An extended source, like the sun or an incandescent light bulb. All right, when we look at that, there's atoms everywhere being jostled and emitting light. Okay, so if we have an extended source, we're going to have many, many emitters. Now they're all doing their own thing. Each one of those emitters is sending out a coherent little pulse of light. But the emission of one of these pulses compared to another one from an atom that was really far away is completely uncorrelated. So we have independent emitters that are emitting light. And even though we have constant irradiation roughly, right? We have a constant irradiation. This is actually due to a bunch of independent little pulses, we can think of it, coherent blips of light from the individual emitters, many, many of them. All right. So this leads to an interesting picture. We can still have a coherence time. We can still have this time of coherence, even for something which is always on, because it consists of light from individual emitters that are each emitting light at their own rate. And this leads to we can model it as a train of coherent bursts. Right? How long does it stay coherent? What I mean is, how long, if we actually looked at this light, under a very short time interval here, it would be a perfect sine wave. But then you would interfere, that would die out, and another atom's light would take over, and it would be mutually coherent for some time before it kind of blipped out again and started. So there's going to be individual times, we'll call it tau or tau c, over which there's a fixed relation between where this maximum is and this maximum and this maximum. After a while, there's no longer going to be a relationship. It's going to be a completely random whether or not this the field at this point is a maximum or a minimum or somewhere in between, because it's due to incoherent emission, or rather uncorrelated emission from an extended source whose individual atoms are doing their own thing. Okay? And this leads to the concept of a coherence length for actual continuous light that is always on, right? If it consists of incoherent emitters. What is that coherence length? Well, it's just related to the spectrum of the light, right? So the coherence time is proportional to 1 over the bandwidth, as we call it, the spread in frequency of the emission of the light, okay? And we can just apply this to a coherence length. So C times the coherence length is, we'll call it C times the coherence time is what we call the coherence length. And that's, well, just C over delta omega. So this tells us that if I have light, here's a laser, it has some coherence length, there's going to be a length associated with this based on the bandwidth of this laser. Now, we can actually calculate how long it is. I haven't done the calculation, but I think last lecture we mentioned that the bandwidth is likely 100 megahertz or something like that. So for a laser, even a pretty cruddy laser, delta omega is on the order of 10 to the 8 per second. So C over delta omega, which is our coherence length, is going to be on the order of 3 times 10 to the 8 divided by 10 to the 8, at least 3 meters. And this is a pretty bad laser. Most lasers in the lab will have coherence lengths of hundreds of meters or kilometers. On the other hand, light from a light bulb will have a bandwidth which is spanning terahertz, 10,000 to a million times more than this, and it's going to have a coherence length, therefore, which is 10,000 to a million times less than this of microns, right? So if we have like a light bulb or something like that, basically you can go a wavelength or so before we start losing coherence. All right, so we need a very narrow band. LEDs will have somewhere in between, but a laser can have a very long one. Next week, we're going to talk about interferometers, and I want to wrap it up with this. I want to wrap it up with something we're going to justify a bit more next week. How do I measure this stuff? How do I know whether or not I'm coherent? Remember, if I have two sine waves, and they're perfectly in phase, I can use the superposition principle, E1, E2. I can just add them up. So E is equal to E1 plus E2, okay? And at all times, they're waving up together and they're waving down together. So I'm just going to get a sinusoidal wave, if they're completely lined up, which is twice as big. And remember our intensity? It's 1/2 epsilon naught NC times E squared. So if each one of these has the intensity I, if I add them up, I'm going to have that going to E1 plus E2, so 2E times the stuff out front, which is 4 times the original intensity. On the other hand, I can be completely out of phase. They're completely out of phase, such that one's a max when the other one's a min, and if I add those up, I'm going to get 0 everywhere. So the intensity in this case is going to go to 0. So I can get intensities between 0 and 4 times the individual intensities of the beams. That's because if things are coherent, I'll write it up here now, things are coherent, the fields add. We can just add the fields. But this does not hold if we have incoherent light, right? Because there's one thing we kind of have been lazy about that we wrote in the very beginning that I have to put in here. The intensity, right, is the time averaged field. Remember the field moves at, goes up and down at 10 to the 14, 10 to the 15 times per second. So we don't have detectors which can move fast enough to detect this, and certainly not our eyes. So we're always measuring the average intensity. What happens if we have this incoherent light pulses? So one is mutually incoherent, it jumps, and then it jumps, and then it jumps. If we add these two things up, sure, they're going to start constructively interfering, but it'll randomly jump to destructive interference and somewhere in between, and we'll just get some kind of weird overall in-between picture. And if we, pardon the mathematical non-rigor here, if I take the average of this sum here, there's no adding of maximum or minima, and basically what we're just going to see is the two fields as if there was no coherence, as if they're not adding up like waves. We're just going to get I will always go to I1 plus I2. So if they're equal, I will go to 2I naught. Okay? So this is something we're going to mathematically prove next week, but it's just something I wanted to talk about. Next week we're going to actually look at interferometers, which can actually measure this. So just as a rule, coherent light, you add the fields and do all the math. Incoherent light, you have to treat it a bit differently because we don't have all this superposition. Well, we have superposition, but we have superposition of mutually random signals. So it's the intensities that add in this case. Okay, so that was just a sneak peek at next week. I did not mean that to rhyme. So it's a sneak peek of what we're going to be doing when we look at interferometers. And that's it for this lecture. I just wanted to go through the essence of coherence theory. So just to summarize, let's have a look at what we did today. Okay, so the first thing is that the time domain and the frequency domain are related through Fourier theory. The tighter we squeeze the temporal duration, the wider the range of frequencies that corresponds to. If I have a purely monochromatic, I squeeze in all the frequencies, the pulse will become infinitely long. Okay, we saw that. We also looked at a way that we could talk about the time and frequency domains, which was a very powerful analysis that allowed us to kind of build up an intuitive picture of what was going on, either in terms of things that were happening in time or things that were happening to individual frequencies. And the fact that these individual emitters were emitting their own little coherent blips that lasted for a finite time, if we have an extended source that has these independent emitters of light, we're going to have little blips of coherence, little trains of coherent radiation, which will randomly change phase and then go to the next little blip of coherent radiation, and so on and so forth. And that in time will, if we just multiply that by c, corresponds to a physical length over which the beam is coherent. Okay, that's going to be very important next week when we talk about interferometry. But that's it for this video, and that's it for this week. So great work, and we will see you next time.